Hi there, welcome to lesson 2 of simple harmonic motion, where today we're going to look at what makes simple harmonic motion simple and harmonic. So if we dive straight into some algebra, if you imagine you've got the situation of a mass spring system, for example, so you've got a spring hanging from the wall, there you go, and we've got our little mass there. That looks terrible because I was looking at the screen instead of my drawing, oh well. And then if we displace that slightly, so maybe we pull it down a bit, so it's down here, then we've got the sort of extended spring part there. And the force on that is going to be in an opposite direction to how we've displaced it, isn't it? The spring is going to be pulling that back up. So even though F is that way, the force downwards, the force is upwards, which is opposite to our displacement downwards, which we call the displacement X. And likewise, if you sort of let that play through half an oscillation, if that then displaces itself back up here, for X to be there, we've then got our opposing gravitational force, so weight of the object mostly, and some tension in the spring as well, pulling it back down. So the force is in the opposite direction to X again. We know that because we know Hooke's law. And if we assume all of these are spring systems that obey Hooke's law, so we know that F equals kx. We've done that before. But actually, that just tells us the magnitude of the force. It doesn't tell us the direction. The direction is opposite. So F is negative kx. Yeah. And because of my mate Isaac Newton, we know that F equals ma. That colour isn't very nice, is it? Oh well, let's stick with it. Let's commit. So we know that because F is proportional to A, we know that A is proportional to minus kx. And this here is what defines simple harmonic motion. So that if acceleration is proportional and in the opposite direction to displacement, so proportional to x and opposite direction to x, that's what makes simple harmonic motion a simple harmonic motion. If that is the case, we have SHM. We can take that a little bit more mathematically. So actually we know that A is the rate of change of the rate of change of displacement. So that's what d squared x by dt squared. Or d, I can't remember when you're supposed to say squared and when you're supposed to say 2. Haven't done proper hardcore maths for a while. And therefore we've got this equation here where x is proportional to, or let's say negative x is proportional to the second derivative of itself, which is that's something called a differential equation. And if you do some much more horrible maths than I am prepared to do live on a YouTube video, then you can get to where we're going to get to next by processing it that way. However, we're going to pretend we've done all that, and we've just done it experimentally, and we've made some observations, and then we can see, actually, what does that displacement look like over time. So, if we plot a graph of displacement over time, so let's call this axis x, where this is positive and this is negative, okay, and then we're going to have our maximum displacement here and here, so let's call that, we can call that the amplitude, A, and negative A. So at time 0, we can say that the amplitude is at its maximum. Yeah. And then one time period later, that is going to be here again. So if we call this here the time period t, yeah, and then this here could be time period 2t again. So we know that another time period later it's going to be that. We know half a time period, assuming we've not got any energy losses, these are free oscillations, half a time period after the initial displacement, it is going to be at the maximum negative displacement, so it's going to be here. And a quarter of a time period afterwards, we know that that's going to have gone a quarter of an oscillation, so it's going to have reached to the equilibrium point, and hopefully you see where this is going. You might have predicted it already. So we've got this lovely sine wave here, which is probably not going to look great when I draw it. Oh well. And that is, actually it's incorrect for me to call it a sine wave, isn't it? Because it starts at the top. That's a cos wave, a cos pattern. And actually, we can see that the maximum of the cos function normally goes up to 1. Here it goes up to a, so that's 1 multiplied by a. So actually we have this equation in simple harmonic motion, x is equal to a cos. Now this is a little bit harder. If we make this phase, so this here is 2 pi over t times t is 2 pi. Yeah, so this is actually our omega t on here. So a cos omega t, so a times the cosine of this function of t. Yeah. Now, if we do velocity, we know that velocity is the gradient of a distance time graph, or here a displacement time graph. I'm not going to actually label these parts yet. And so the gradient at the very start here is 0. And then its maximum negative gradient is a quarter later, and then it's back to 0 again. So we've got 0, maximum negative gradient, back to 0, maximum positive gradient here, and then back to 0. So if you can see where that's going, let's just repeat that pattern again. Yeah, we can say that this here is going to be this shape. And this does look more like a sine function, apart from it's going negative at first. So this is a negative sine function. And actually, this goes all the way up to a omega and a omega. And we can prove that with a little bit of maths. So if we've got, let's just do a little aside here. So if you have y is equal to cos of f of x, then dy by dx, the derivative of that, is actually the derivative of f of x times by minus sine of f of x. So what's inside the brackets doesn't change, but you take its derivative and take it outside the brackets to multiply it by your sine. Yeah. And if you've got sine, it goes to cos. Yeah, so cos goes to minus sine goes to minus cos will then go to plus sine will go to plus cos. So if we take that there, our velocity can be given as minus a omega sine omega t. And then if we do one for oops, there go my keys. We do one for acceleration. What a lovely shade of pink that is. Our acceleration here is going to do the same thing. We know that acceleration is the derivative of this. So if we take the derivative of this with time, that becomes omega. Take that to the outside. Minus a omega times omega is minus a omega squared. So we've got, oh, sorry, that shouldn't be a capital A, should it, for acceleration? There we go. So minus a omega squared times cos omega t. And oh look, we've got a sine function again, a cos function again. Look, this here and this here, they look very similar, don't they? And actually, we can do some substitution here of this a cos omega t and a cos omega t. So we can actually put that in as a is equal to negative omega squared x, which agrees with this acceleration is proportional to x, and it's in the opposite direction to x because of this negative sign. And let's just, for the sake of completeness, draw our little sine, cos graph on. So maximum negative at first, then 0 gradient here, maximum positive a quarter later, then 0, then back to maximum negative, and repeat that pattern. Go to the periodic function, and we get this lovely minus cos function, the maximum and minimum of which are going to be a omega squared. Oops, I realised I missed off a negative sign earlier on. There we go. So those are two ways of getting to this definition of SHM. And we know that if we've got any situation where acceleration is proportional to negative displacement, then that is what defines simple harmonic motion. let's have a go at a problem which doesn't actually use any of this cos stuff, it's just going to use a definition. So, we've got this problem here. We've got a lovely rubber duck in a bathtub, bobbing up and down, which is an example of simple harmonic motion, anything bobbing in the waves of water. And it tells us a time period of 3 seconds and an amplitude of 58 millimeters. And we have to find angular frequency and maximum acceleration. So, if we start with A, angular frequency is nice and easy. Omega is 2 pi over time period. And 2 pi over time period is 2 pi over 3.0, which, not done in my head because I don't know pi that well, is 2.094, should we say, or 2.09 rads per second. And I'm just going to save that in my calculator actually, if I can remember how. No, there's not that. Store that as A, I think. There we go. Let's keep that in there because we're going to need that for later on. And then part B, it's maximum acceleration. So we know that A is minus omega squared x. And the maximum acceleration is going to be when displacement says maximum. So that maximum displacement is A. So we can actually just say our maximum acceleration is minus omega squared, so minus 2.09 squared, times our amplitude, which is 58 millimeters, or so 58 times 10 to the minus 3 meters. So let's type that in. I've stored our acceleration as A, so that is that. So our acceleration squared, not acceleration, sorry, angular frequency. I've stored our angular frequency as A, confusingly. So that squared, negative that squared, whoops, times by 58 times, oh, I'm messing up the powers all over the place here, times by 58 times 10 to the minus 3 gives us negative, or can ignore the negative to be honest, because we're only asked for the magnitude, aren't we? We're not really asked for direction here. The magnitude is going to be the same no matter what. 0.25 meters per second squared. So there's our answers. So, hopefully that makes sense. I will see you next time.